Reaction rates in chemical equilibrium. Section 13, rates of reactions. So here we're talking about how fast reactions occur. All right, we can write a chemical reaction, but that doesn't tell us how fast or slow it's going to occur. So we're going to look at what are some situations that would make a reaction go faster, slower, stuff like that. Right? So all of this, rates of reactions, is sort of governed by this idea of a collision theory. So the collision theory states that the molecules have to collide in the proper orientation, and when they collide, they have to have enough energy for the reaction to occur. Okay? So let's look at the idea of proper orientation. Right? So in this reaction, nitrogen and oxygen combine to form NO and NO. Now, notice nitrogen and oxygen have to collide. Nitrogen and oxygen have to collide in order for the reaction to occur. Right? So what happens if they don't have enough energy? Well, in this situation, A, they don't have enough energy. So they collide correctly, nitrogen, oxygen, but they don't have nearly enough energy, so they just bounce off of each other. They have to have enough energy for the nitrogen bond to break and for the oxygen bond to break. Okay? In part B, or in reaction B, they collide with the wrong orientation. There's one nitrogen-oxygen collision, but not this second one. And so again, they're just going to bounce off of each other. And so in C, again, incorrect orientation, so they're just going to bounce off of each other. So let's look at that collision that actually works. Nitrogen, oxygen, they collide correctly, and they collide with enough energy. So colliding correctly is pretty obvious of why that's going to stop a reaction. But let's talk about why molecules have to have enough energy. In every reaction profile, right, looks like this, every energy profile, energy diagram, we're going to see reactants, right, like that, and then they're going to collide correctly, and then once they collide, their energy is going to go down. Now this hill, so this hill, we start here, here's the height. That hill is what's called the activation energy, and that's the amount of energy that's required for the reaction to start. Alright, let's talk about one other thing here. We have, here's the amount of energy, the difference in energy for this reaction. So this would actually be an endothermic reaction. Okay. Let's look at what an exothermic reaction would look like, paying particular attention to the activation energy. So let's draw one over here. We've got energy on the y-axis. Okay, and then this is the reaction progress. Alright. So again, our reactants are going to start with a certain amount of energy. They're going to require a certain amount of energy for the reaction to happen. So again, that's what's called the activation energy. And then for an exothermic reaction, they're going to end up with less energy than what they started out with. But this amount of energy right here, this is still the activation energy. Okay? It's often given the symbol of E sub A, activation energy. Now, right at the top, there's a couple things that you need to know about. This is what's called the transition state. It's also called, again right here at the top, so it's called the transition state. It's also called the activated complex. And it may even be called the intermediate. And the intermediate is the actual molecule that forms temporarily. Transition state, the actual molecule. Activated complex, the actual molecule. But it forms right there where they collide correctly with enough energy. Okay? So again, 3 conditions required for a reaction to occur. They have to collide correctly, they have to have sufficient amount of energy. We actually measure the rate of reaction by measuring the amount of a reactant used or amount of product formed in a certain period of time. What all affects the rate of reaction? The temperature can affect the rate of reaction. the concentration of reactants can affect the rate of the reaction, and the presence of a catalyst. Okay? An increase in temperature will speed up the rate of the reaction. Let's talk about why. For that, we're going to look at what's called a Boltzmann diagram. Okay. So in a Boltzmann diagram, you're always going to have somehow some measurement of particles on the side. Okay, some value that measures particles, and then on the bottom you're going to have energy. Okay. For us, we can talk about kinetic energy. And so what we see is that particles, remember, temperature is an average of the kinetic energy, right? And so what we'll see is that at a certain temperature, let's say the temperature is equal to, let's say it's 273 degrees Celsius, so 273 Kelvin, pardon me. Okay, so that'd be 0 degrees Celsius, 273 Kelvin. What we see is that we have a wide range of kinetic energies, right? It's not just one kinetic energy because it's the average. But this line right here, that line represents the activation energy. So this is the amount of energy needed, the minimum amount of kinetic energy needed in order for this reaction to occur. So we can see at this temperature only the particles that are bounded in that red area will have enough energy for the reaction to occur. Now, what happens if we increase temperature? Well, if we increase temperature, we're shifting our average over. So we're still going to have some slow-moving molecules down here. Okay? But the number of molecules with that higher amount of energy is going to shift. So now we see the molecules bounded in the red and green will have enough energy. And so let's see, that was the first, that was initial energy. Now the second energy is going to be greater than 273 Kelvin. More molecules are going to have the required energy to react. Okay, so let's see. Increased temperature makes the particles move faster because of higher energy. That means we're going to have more possible collisions. Okay, think of speed dating. If you go on one date, one night, you can only have that one date. But if you go on, let's say, 10 dates in one night, you have a greater chance of causing an attraction to occur, right? Now, but the big thing, and this is one that students always forget, they always say, oh yeah, more possible collisions. Well, the real big difference, the increased energy means more molecules have the proper activation energy. And so more molecules are going to be able to react. Alright? So that's an increase in temperature. An increase in temperature causes the reaction to happen faster because more molecules have the required activation energy, and it's possible we can have more collisions. An increase in concentration speeds up the rate of the reaction as well. The reason why is because now there are more reactants, which means more possible collisions. Take a look at this picture. So in this case, here's the reaction. Blue has to combine with orange. If there is only one blue and one orange, then you can only have one possible collision. If there are two blues and one orange, you can have two collisions. So now we've increased our chance of collision. Now take a look if you have two blue and two orange, so we've really increased the concentration. Now we can have four possible collisions. So this is, again, if we go to the dating analogy, if we go to a party where there's only one girl and you're a boy, or you're a girl that's interested in a girl, whichever, then there's only one possibility there. But if we go to a party where there's lots of boys and lots of girls, there's a greater chance of an attraction occurring. So this is the idea of like singles only parties, stuff like that. So we looked at increasing in temperature, we looked at increase in concentration. A catalyst also speeds up the rate of the reaction, but the reason why is because it provides a different pathway that has a lower activation energy. Okay? So we don't lower the activation of that pathway, we create a brand new pathway. So here is the original pathway in green. Now our new pathway in blue is lower. Okay? Let's go back up here to our energy profile. So red was the original activation energy. If we do a new reaction, or if we use a catalyst, we can lower the activation energy. So now here's the activation energy with a catalyst. Okay, so that would be a Boltzmann diagram of what happens with a catalyst. If you look at the reaction profile here, you can see the green is the original activation energy, the blue is the new activation energy, which is a lot less. More particles are going to have it. So now let's talk about grades. If it's a 90% to get an A, if I lower that to 80%, don't change anything else, I lower it to 80%, more people are going to have an A because I've lowered the threshold for that to happen. Alright? Neat thing, catalyst is not used in a chemical reaction. And biologically, we call it a catalyst an enzyme. I've just thrown that out there. Okay, so there's the collision theory and how we can increase the rate of a reaction.